All right, so this week we're going to continue on linked lists and list-based data structures. We started talking about linked lists last time because we already identified a use case in which an array-based list had terrible performance, where we have, say, like 1 million elements in the array list, and we want to insert something at the very beginning of that array list. That entailed shifting 1 million things down just to accommodate that one thing. With a linked list, everything is stored as a node. So you don't have this big contiguous array that you have to shift around and do anything with. Instead, it starts at the head, right? You've got a node here that is at the front of the list. At the end, we use the terminology tail, but for this particular implementation, we're not going to be keeping track of that. That is a variation we'll talk about later. But otherwise, each element is stored in a node, and each node has a reference to the next node in the list. So therefore, to traverse a list or to get a particular element, what you do is you start at the head and then you traverse to the next, to the next, to the next, to the next, until you get to the end here. The end here for us is going to simply be null as far as Java is concerned. I'm using a placeholder here, phi, to indicate that that's the end of the list. Okay? All right, so that's where we're going to pick it up from last time. We decided that we're going to go ahead and keep track of the size, and anytime that we add an element, we're going to increment this. Anytime we take away an element, we're going to decrement this, so that we don't have to recompute it every single time that we want the size. All right, we've got a nice constructor here that sets up an empty list of size 0, and the head here will end up being null. So let's go ahead and get started with the 4 basic operations. We need a way to add things. We need a way to retrieve things. We need a way to remove things. We need a way to modify things. All right? So let's go ahead and start with this add element. Remember that this is going to adds the given element x to the end of the list. ... So what's our first step here? Right? We've got to find the end of the list, right? Find the last node. ... All right? Why? Because let's visualize this. How is it going to work? Well, first of all, I'm going to go ahead and create a brand new node, right, with x in it. So let's suppose that that x is just simply 42. Okay? That 42, next, by default here, it's going to start pointing to null. All right? How do I add that to the end of the list? Well, first of all, I have to start at the head of the list. I'm going to get that node, go to the end, next, next, next. Once I have this node right here, what do? I simply make this, instead of pointing to null, I make it point to the end of this new node over here. Right? And then, just like a chain, right, because it's a linked list, it's chained together, go ahead and pull it taut, and you'll have that new node at the end of the list. Okay? So, let's come back over here and outline that. First of all, we need to find the last node. Then we need to create a new node. In fact, you can do that in any order. Let's go ahead and move that up to the top. Okay? So let's go ahead and create a new node, find the last node, and make the last node point to the new node. All right? That should be pretty straightforward here. Let's go ahead and create the new node. Right? If you want to label these as 1, 2, and 3. How do I create a new node? Well, that's just a constructor call. Node holding elements of type t, and I'll call this the new tail because that's where I'm putting it. I'm putting it at the end. Remember that we called those the head of the list the head, and therefore the end of the list the tail, just like a snake, head and tail. So my new tail here is going to be new node containing an element of type t, and that element is going to be x. All right? I've got this brand new node. Now by default, this method here, right, next is going to end up being null, and so we're good on that. Otherwise, it takes that element and assigns that element to that node. Okay? Find the last node. Uh-oh. I don't know how to do that yet. Right? Make the last node point to the new node. Okay? So let's find this last node here. Okay? Gee, I'm looking to look forward here. I'm going to look forward to all these other things. Add element to the start. I'll probably want that node so that I can add it to the new start, right? Replace element at index. Well, if I'm going to replace an element at the index, I'm probably going to want to find the node at that index. Remove element at index. Well, if I'm going to remove an element at a particular index, I'm probably going to want to get the node at that index. Do you start seeing a pattern here? Maybe we want a function to help us out here, a convenience function. So before I even come up here and find the last node, let's go ahead and think about how we might create a function or a method that retrieves the ith node, right? So public node t, get ith node, right? Something like that. I'll go ahead and call it get node at index. Right? And then I'll go ahead and take an index. There we go. Okay. Get node at index. How do we do that? So you want the one at the 0th index. Well, if index is equal to 0, then I'll just simply return this dot head. Right? If you want the node, else if index is equal to 1, what will I return? This dot head dot get next, right? You want the second one. Do you start seeing a pattern here? Else if index is equal to 2, then I will go ahead and return this dot head dot get next, right? I'm chaining them together, right? Now, is this a good pattern to follow here? Well, if you only want to support a finite number of things, then yes. What should this be screaming out to you? What kind of a control structure are we probably going to want to define here? Oh, let me make sure. Yep, we're good. Right. So you want the ith of something. I probably want to go into some sort of a loop, right? While loop or a for loop? Which one? When do you generally use a while loop? When you don't know how many iterations you're going to be going, right? While these two numbers are very far apart, and then they get closer and closer together because there's some convergence, right? I don't know how long it's going to take me to do that, so I'll go for a while loop. When do you usually use a for loop? When you know how many iterations you're going to run, right? If it's going to run for 5 iterations, or 2 iterations, or for n iterations, or for index iterations, then I'll probably use a for loop. Right? For int I equals 0, I is less than, say, index I++. Right? What I'll do is I'll iterate to the next node. Right? In fact, I'll not iterate, but I will traverse to the next node. So where do I start before my for loop even begins? I'll need a node called the current node. Where do I always start? Where's the only place I can start? At the head. Now suppose that index is 0 here. Will this for loop execute at all? Nope. So what's your current right now? The head. That's exactly what you wanted, right? Index 0 is going to be the head. Index 1 will traverse to the next node, so current is equal to current dot get next. If this is 5, right, then you want the, or let's say 4, then you want the element at index 4. How many times do you iterate? 1, 2, 3, 4. Right? Nice pattern here. And I will return current. There, that gives me the ith index. Okay? So, how do we find the last node now? This dot get element at index, this dot size. Is that correct? Let's think about that. So if the size is 5, there are 5 things here. Or let's look at this picture before we even began. The size here is what? When this is initially pointing to, oops, I didn't want all of that. The size is 4. There we go. And so which one do you want to be the last one? 0, 1, 2, 3. So we need to subtract by 1 here. Right? This minus 1. I've got the last node in my hand right here, right? As long as I capture it into a variable, actually. Node t last. Or I'll just call it tail because that's what it is. There we go. Now I need to make the tail point to the new tail. So tail dot set next. Remember that we had a very good reason to have a setter when we designed that node because we want to update the next node to the new tail. There. Let's return. You don't have to explicitly do that, but sure. Oops, what's wrong? oh, not get element at an index, but get node at index. There we go. Autocomplete just called the wrong one. All right, let's open up this demo and see if we can get it to work. I do not want 100,000 elements, so let's just go ahead and go with 10 elements here. And I will go ahead and uncomment that. And let's go ahead and change this so that we're adding it to the end. Dot add element. And then we'll go with I plus 1 times 10. So let's kick this down to 5 to keep it manageable. Right? So what am I going to do is I'm going to insert 10, 20, 30, 40, 50. It's going to look something like this. Okay? If we want to, we can kick this down to 4, and it'll look exactly like this down at the end of that run. Okay? Let's run it. There are lots of problems that we're going to have to deal with here. Right? Design problems and correctness problems. Uh-oh. Cannot invoke tail this method setNext because tail is null. What happened? Well, first of all, what kind of tool should I probably be using to find out what happened? The debugger. So let's go ahead and set this as a breakpoint. Let's go ahead and debug it. Switch to my debugging perspective here. Remember that this 0 down here is because of this line right here where we're printing out the size. Okay. And let's go ahead and go into that. Let's go ahead and go into that, except I think it's going to probably take me to the integer. Yeah, I don't want that. So let's go ahead and jump into the add element method. Okay. Now let's take a look around. We are inserting 10. X is 10. Okay. Now I'm going to go ahead and create a new node, tail node, containing element 10. That works. Okay. Let's go ahead and go to the next line here. Actually, before I go to the next line, let's go ahead and go into that function there. Get node at index size minus 1. What was the size again? We printed it right here. Or we can look at it up here. This dot size is 0. 0 things. So let's go ahead and go into that function there. Step over that, and because there's nothing in the list yet, what is current? Null. Okay. That means that this loop will not execute, just like we predicted. It will return current. So what is current at this point? Tail. Null. Right? Can you set the next value of a null object? Can you invoke any methods on a null object? No. All right, so we've isolated what's going on here. When the list is empty, this isn't going to work. So suggestions. That's one of those corner cases, one of those edge cases, where you, for example, down in our toString method, oh, we didn't have a toString method here yet, but we will eventually. You don't want to print the last comma in a list or something like that. That's an edge case. You don't handle that in your loop. Instead, you handle that separately. So if having an empty list is an edge case, we should handle that separately. If we have a list that is empty, what do we have visually? Here's the head, and it is pointing to null. Can I add it to the end of that list? No, because there's no beginning to that list. So what do? I create a new node, and I make head point to that new node. That's easy enough. We've already got the node. So, 2, if the list is empty, make head point to this new tail, ... Okay? So, if, how do I know the list is empty? If this dot size is 0, right? Then I know that it's empty. Okay? And so this dot head is equal to new tail and return. And you're done. Right? Maybe, maybe not. Otherwise, if it's not empty, then you've already created the new tail, then you can go ahead and get the element at that particular index and set it, and you're done. Okay? Let's come over here to the demo and see if it works. Oh, no exception now. How do I know if it worked or not? I don't know, right? Let's go ahead and print it out. I'll go ahead and add here we go. System.out.println numbers. Let's print it out and see if it worked. Poor man's debugging. Oh, did it work? We don't have a toString method here, right? So let's go ahead and set another breakpoint, unset this one, and let's go ahead and run this program up to that point. Let's take a look at the actual linked list here. Numbers, right? And again, there's no toString method. We've got the head, and the head is pointing to, or referring to 40 here. Okay. Why? Because we added 10. Oh, sorry, it's not going to look like this, right? It's going to, you add 10 to the end, then you add 20 to the end, 30, 40. Oh, I guess something is going on here, right? So we've got something fix. What does the next look like? Oh, the next is null. All right. So help me out here. What's going on? Definitely wrong, right? Remember last time we took on the responsibility of keeping track of the size so that we didn't have to recompute it every single time? We're using that here implicitly. Give me the element at size minus 1. Are we ever updating the size? Anytime we add something, we need to what? Increment, 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 increment. Anytime we take something away, we need to decrement, 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 decrement. What am I not doing here? I'm not increasing the size. So this dot size plus plus, if it's the head. Otherwise, this dot size plus plus there. You could go ahead and reduce that down to one liner up here, right? But you really haven't added it yet. You've added it as far as this line is concerned, so then go ahead and increment it. You've added it as far as this line is concerned, so then go ahead and increment it. Right? If you want to save on one line of repeated code, then go ahead and put it at the top. But I like to put it after the end, after I'm assured that I'm not going to use it anymore. Let's try this again and understand why it was not working before. So let's go ahead and run the debugger now. Right? Here's the head, and its element is 10, just like we expected. It is pointing to another element, 20. It is pointing to the next element, which is 30. It is pointing to the next element, which is 40. And what's the next element? Null. You can see your linked list visualized right here in the debugger. That points to that, points to that, points to that. Pretty cool. And it works. Right? Let's go ahead and stop that now. And now I do want to take care of this. Okay? Actually, before we do that, let's think about one design issue here. Okay? Let's run this again. Yeah, it's working just fine. Let's go out of our debug perspective here. All right, oops. And let's collapse this so that we're not staring at it all the time. There we go. All right, so public get node at index, okay? Does that sound like it should be a public method? So what is it revealing to the outside world? That we're storing things as nodes. In fact, here you go. Here's the node that we store it as, right? Should the outside world know about the internal workings of our class? No. That is Object-Oriented Programming 101. That is encapsulation, right? We do not want a leaky abstraction by breaking encapsulation here, right? We don't want to reveal this to the outside world. But we really want to use it because we're going to use it down here and we're going to use it there and we're going to use it there. But we're going to use it inside the class. So if we're going to use it inside the class, let's make sure that we're only using it inside the class and making it private. Now it's no longer a leaky abstraction. We're not leaking information to the outside world that this thing is a linked list and that it stores stuff in these things called nodes. And by the way, you can go ahead and screw it up by grabbing those nodes and doing whatever you want with them, breaking encapsulation. All right? So I've made this into a private method. All right. That looks good. That looks good, and we're definitely going to use it over and over again. But before we go on, I do want to do poor man's debugging here because I don't want to have to run the debugger every single time just for ad hoc testing, just for sanity check testing. Right? So let's go ahead and make it so that we're not printing out this fully qualified package name along with a memory address here. Let's actually go ahead and implement the toString method. public, actually let's do it at the end here. Public string toString. All right. I'll go ahead and start with a string builder. Builder, SB is equal to new string builder, because I want to nicely format it, right? And so SB.append. I'll start out with this, this square bracket right here, and then I'll end it with the square bracket and a space to make it all nice and pretty. And then I'll return SB.toString. There we go. Everything in between is me going to be iterating over the list and ensuring that I get each element and concatenate it along with a comma, space, comma, space, comma, space. Right? So we're going to want 10, comma, space, 20, comma, space, 30, dot, dot, dot. Okay? Now, think about this kind of approach. For int I equals 0, I is less than this dot size, I plus plus. Right? This is what you would think about normally if you were thinking in terms of regular old arrays. For each element in the array, what I'll do is I'll get the node. I'll call it u, is equal to this dot get a node at index I, and then I can get its element. U dot get element, right, plus comma and SB dot append, those two things. U dot, there we go. This will work. Let's go ahead and run it and show you. Right? Now we do have that coding Oxford comma right there, right? That superfluous comma. So we could, of course, go ahead and say, oh no, -1, and then we'll go ahead and take care of that separately without the comma. Right? And not I, but this dot size -1. So again, corner cases. You handle this all the time when you write a loop. The first iteration needs to be handled differently. This last iteration needs to be handled differently. Right? Corner cases. Think about this, though. What are you doing every single iteration of this loop? You're starting at the beginning and traversing all the way to I. The next iteration, well, the next one is right next to it, right? But what am I doing instead? I'm starting all the way at the beginning and going all the way again to the end. Have you ever heard of the, it's not a parable, what is it, the kind of a story here, where this guy goes to this other guy and he says, hey, I want you to paint my fence, right? And here's the paint and everything. He goes, great, I charge $10 an hour. He goes, okay, fine, I'll go ahead and pay you $10 an hour here. Starts painting the fence. Comes back a couple of hours later and he's made good progress, right? He's got half the fence done already. Right? So he goes, wow, this is going to be cheap. It's only going to be $40 or something. Comes back a couple of hours later. He's only made half as much progress as he did before. So yeah, it's 3/4 done, but you know, it took him a little bit more. Maybe I'll pay for his lunch break or something like that. Comes back a couple of hours more. He has even less done than he did before. And so he starts to get suspicious and he says, how are you actually painting this fence? Oh, here, I'll show you. So what does he do? He goes to the end of the fence where the paint bucket is, dips his paintbrush, walks all the way over to the part of the fence that he's not yet painted, and starts painting there. Then what does he do? Well, he's out of paint now. So what does he do? He walks all the way to the beginning of the fence, dips his paintbrush again, walks all the way back, right? And this is how he's scamming the guy, right? He's like, why don't you, then the guy just yells at him, why don't you just pick up the paintbrush or paint bucket and walk with it to as you go along here? He goes, I never thought of that, right? But of course, now I've charged you thousands of dollars, right? That's what we're doing here. Does that sound, I mean, if you're charging by the hour, then yeah, does this sound like a good idea? Yeah, if you're charging by the microsecond, if you're a computer, right? That's a great idea. That's a great idea if you're paying for those resources. No. Let's rethink this. All right, get rid of that. What should I do? Something very, very similar to what we're doing inside of this function to begin with, where we start at the head, and then we just simply traverse until we get to the end. So yes, repeated code, but if you didn't repeat that code, you're paying that fence painter way more money than you need to be paying. Right? So the current here And what I'll do is I'll go into a while loop here instead, just for variety. While not at the end of the list, ... what I will do is I will traverse to the next node, but before I do that, let's go ahead and concatenate it. Concatenate the current node, and that will just be simply this sb.append current.getElement with that comma right there. Right? Then traverse to the next node so that you're set up for the next iteration of this. When are you not at the end of the list? When the current node has not fallen off the edge. Right? There's my current node. Go to the next one. Current node, current node, current node. How do I know when I'm done? I've fallen off the edge and current is now phi, or in terms of Java, it is null. So while it's not equal to null, keep traversing, keep traversing, keep traversing. I'm not going to return it. There we go. All right, let's see if that worked. Yep, that coding Oxford comma is there though. I'll let you do that as an exercise. How do you take care of this? You need to make sure that you're stopping one step short of the last node there, and then handling it different. Okay? Don't go back and erase the comma just so that from the string builder here, string builder or sb.erase sb.erase the last two characters. Don't do that. Right? Do it smart. Right? Do it correctly. I'll leave that as an exercise though. Right? Wonderful. We now have the foundation to probably take the rest of this stuff on in the next 25 minutes and be done with it. Right? Why? Because I looked forward and I saw the need to be able to get an arbitrary node here. Right? So let's add element to the start. How do I do that? In fact, I don't even need to get that node. Right? How do I add an element to the start? Well, if I've got a head already, what do? Create 42, right? Make head point to this, and then make this point to head. What if it's empty already? Well, same process. Make head point to this new node, make this point to null, and we're done. Right? This is basically a two-liner. I could get it down to one line. Right? Node t new head is equal to new node element of t holding x. Right? This dot head is equal to the new head, right? And then I need to make sure that the old head points to, or that the new head points to the old head. Dot set next, not the new head, but the old head. Do I have access to the old head at this point though? Nope. So let's go ahead and put it up here. The old head before I reset it was this dot head. There. Let's test that. Right? Don't write a function, then another function, then another function, then another function without at least a minimum amount of testing. Right? Just a sanity check here. Make sure that it actually works. Right? So add element here. I'll go ahead and add element 42. There we go. And print it out. Now remember it was 10, 20, 30, 40, and then if I add it to the head, then it should be 42 at the beginning. Oh, sorry. Add element at start, was it? What was it? Add element to start. At start, not to start, at start, whatever. Right? There we go. 42 is at the beginning. What else should I be testing besides this, though? Corner cases. Make sure that you're testing these corner cases. Now this one, if I add it to the start, right? Then it should be 42 and then 10, 20, 30, 40. What happened to our 42? What do I have to remember every single time I add a node? Size. Plus, plus. There. That's going to be all good. 42, 10, 20, 30, 40. I think so, right? We add it to the start, and then this one adds it to the end. So 42, then 10, 20, 30, 40. Right? That looks good. Did we break anything? We know that we broke something if we do a regression test. Test what you were testing before and make sure it still works. Now we've got two 42s. Still works to me, right? Again, that's okay for ad hoc testing. Just as you go, make sure that you didn't break anything, make sure that it works. This is why ad hoc testing is not at all acceptable in real life, right? I mean, as part of the development process, yes, but as a formal process, no. You would want to put together some sort of a JUnit test suite to make sure that all these corner cases are taken care of. So that every time you go in and you change something, you add something, you make sure that it still works, that you didn't break anything. And the only way you can do that is if you have the same tests that are repeatable. Okay? All right. That's down for now. Replace element at index. Okay. And then return it, of course. So what's my first step? If I want to replace the element at index 2, there we go. I want to get this node and get rid of 30 and add 42 there. How do I do that? What's the first step? Getting the node at that index. Hey, good thing I already did that. Node T, the relevant node U is equal to this dot, get node at index. There we go. Now I can go ahead and say U dot set element to X. Right. I've replaced it. Did I design my node class that way though? Apparently not. I made sure that that element was final. You can't reset it. So maybe I now have a very good reason to be able to change these things. At least in my book, that doesn't raise enough, high level enough that it's a very good reason. That's a somewhat okay reason, but it's not a very good reason. Right? Especially when there's another way that you can do it. Right? How am I going to do it over here? I'm going to create a brand new node with the element 42 in it. Right? And what I'm going to do is now that I've got this node, what I can do is I can make this node point to this one, and I can make this node point to that one. Pull the chain tight. What happens to this node effectively? It's gone. Right? We go from here to here to here and to here, taking that detour. Okay. So do I really want just this node right here? I want this node and I want this node on either side of it, because I'm going to make the previous node here point to this new node. I'm going to make this new node point to this node's next node. So all we need to do is make sure that we're getting all the nodes proper here. Right? There's that node at that particular index. Let's go ahead and create that new node. Node T replacement is equal to new node T. Don't need that. There we go. All right. And what I'll do is I will make replacement dot next, or set next, right, equal to u dot get next. Right? That does this part right here. Here's my replacement node, and I'm making it point to that node now. Now I need the previous one here to point to this new node. If you just have this node, though, can you traverse backwards? No, not the way that I've designed it. You can only go one way. So maybe you want to design another different node that does go both ways. A bidirectional node here. Right? That's a variation that we'll talk about later. Let's live with the design that we started with. Ideas. How do I get the previous node? I'll call it previous. It's going to be where? Index -1. Right. There we go. So I've got the previous one, I've got the current one, and I've got the next one using .getNext. Did I need to do that twice? Remember, what's that doing? It's starting at the beginning and traversing all the way to the index. Then you're doing it again to go to index -1. What if I had done this first? Previous. And let's rename this to current. Right? The actual node that you're looking for. Do I need to call that method if I've got the previous one? Nope. Just go next. There's the replacement. current. There we go. And I will make the previous dot set next to the replacement. There. We're all done. Except that, remember the current here, the reason I'm storing that is because I need to return that value there. Return current dot get element. There we go. That should work. Let's go ahead and run it well, we need to give it an actual test case here. What I'll do is I'll take out those 42s. I'll isolate this, this behavior right here. And let's go ahead and go with numbers.replace. What element do we want? The element at 2. Replace element at index. So what was it? We'll replace 30 with 42. Right? So let's print it out before and let's print it out after to make sure that it works. Right? There's 30. It's been replaced with 42. Works. Let's make sure int y is equal to that. And let's actually print out the thing that we replaced it with. I would expect that to be 30 right there. That looks like it works too. All right, done? Or what should I be testing now? Corner cases again. What if you wanted to replace the element at index 0? Are we going to have any problems with that? It didn't work. No exceptions thrown. Okay, that's curious. But did I replace the element at the beginning, which was 10 here? Nope. So we've got a bug there. What about the last one? Element at index 3. We'll replace 40 with 42. That works. Okay, I'll accept that. What about -1? What should happen here? Is that a valid index? Nope. It worked. Right? So maybe it is a valid index. What about 4? Is that a valid index? Nope. Oh, it threw an exception. Right? So neither one of those works. Let's go ahead and think about how to handle both of those to begin with. If you ask for something that doesn't exist, what should I do to you? If index is less than 0 or index is greater than or equal to this dot size, you cannot replace an element that doesn't exist. So I will throw a new, I don't know, illegal argument exception, invalid index. You should not be getting back a null pointer exception. You should not be getting back no information at all and it just fails silently. Right? Instead, you should be getting back a verbose error message here telling you that that is indeed an invalid index. Just like -1 is an invalid index. Right? But 0 is a valid index. Okay? Why is it failing here? Oh, here, let's test 1. Do we get the same results when we actually do want to replace 20 with 42? Yeah, that works. Right. 3, we'll replace the very end. We already did that one. But it doesn't work in this one corner case, right? This edge case here. So what could we do here? Handle it differently. Right? Else if index is equal to 0, that's a very special case of you wanting to replace the head, right? Which you're going to have to do because the head is a different element entirely. Right? So we want to replace the head, ... Right? Otherwise, it seems to work in all of those other cases, so we'll go ahead and do this. There we go. I'm just handling these things differently depending on the input. So we want to replace the head. I will go ahead and create this new node, this new replacement node here. Right? I will save off that value, head dot get element, so that I can return it. X. Oh, I can't use X anymore. I need to use Y. Right? There we go. My replacement node here now becomes the new head. So this dot head is equal to replacement. Right? Except that, what did I forget to do? This replacement, what is it pointing to as a next? Nothing yet. What does it need to point to? Replacement dot set next to this dot head dot get next. Right? And again, visually here, what am I doing? All I'm doing is creating a new node here. I am making it point to the old head, or sorry, the old head's next, so this one right here. And then I'm making head here point to this new one, effectively cutting that old head out of the entire list. Let's see if it works now. Remember, it didn't work before because we ended up replacing 20. Now we're replacing the beginning. So handling edge cases, handling corner cases, testing for them most importantly. What about remove element at index? It's going to be exactly the same, except that there's no replacement, right? So remove element at index. Let's go ahead and grab most of this code. Bad practice, but I'm in a hurry. There we go. So we will throw an exception at you if you ask for something that doesn't exist. Otherwise, if you were wanting to remove the element at the head, then what do? Let's go ahead and get rid of all, let's go ahead and grab the element that we want to, return. Right? And by the way, why is this safe? What if it was an empty list? What about one of those other corner cases where it's an empty list? The size is 0. You asked for 0, which is greater than or equal to 0. We would have thrown that back in your face already. Right? So I know that the head exists at this point, right here. Right? So I'm going to return that element, and then this dot head is equal to this dot head dot get next. That's it. What about remove element at an arbitrary index? I'll go ahead and get the previous, the current, and then maybe the next. Current dot next. Right. So now think about this before we finish this off here. Right. Here is what I've got so far. Here's the previous, here's the current, and here's the next. It looks something like this. All I want to do is cut this middle guy out right here. I want to cut out the current. It's just a one line of code. What do? I make the previous no longer point to current. I make it point to next. Now those coming from a C background, what about this node right here? It's taking up some memory. What would you have to do to make sure that you're taking care of that in C?
Either free or relic.
Free it up, right? So do you need to worry about that in Java? Do you need to worry about garbage collection in Python or Java? Nope. Simply just losing that reference is enough for the garbage collector to pick it up for you. So it's going to be one line. In fact, we're probably going to be able to get rid of some of these variables here. Previous dot set next to next. Actually, we're not, because I'm going to then return current dot get element. There. Come back over here to demo. We didn't break anything, right? But obviously I'm not calling the correct value here. So numbers dot remove element at index. Let's make sure that it works. -1. We should expect an exception back. We do. 0. We should expect 20, 30, 40. We do. Remove the second element. I would expect 10, 30, 40. Yep, yay. 10, 20, 40. Yay. 10, 20, 30. Or 10, oops. I don't think I've been saving, sorry. I've been too quick on my clicking and not quick enough on my keyboard. Let's go ahead and do that again. There, now I'm taking away 20. Now I'm taking away, save, 30. Now I'm taking away 40. All good. 4. Now I should get an exception. There we go. All works. And you see how you can automate this stuff by writing proper unit tests, right? You could put in 1,000,000 things and make sure that it works with 1,000,000 different things, right? And 1,000,000 different combinations. In fact, you could write code that generated every single possible permutation of any list of size 10, right? And then test every single eventuality. You write code to test code so that you're not doing this by hand, and certainly not having to write them out. Here's my 50 different tests. I had to write, cut and paste, cut and paste, cut and paste, cut and paste 50 different times. Right? All right. Wonderful. 5 minutes left. Can we get the rest done? Get element at index? We can get that done in 1 second. How? First of all, let's grab that code. Right? If you ask for something that doesn't exist, we'll throw it back in your face as usual. Otherwise, for all other things, what do? This dot get the node at that index dot, or index dot get element. That's it. Why? Because I had the forethought to write one general function that I knew that would be useful at least in one spot. It's turned out that it's going to be useful in at least 3 or 4 different spots. Right? What's the last one? Add element at index. Right? Probably going to be very, very similar to replace element at index. Right? In fact, you could rewrite this so that you are removing that element and then adding it back in. In other words, 2 function calls. You could take all this code and throw it away. Right? I wouldn't do that, though. Right? Add element at the index. Okay? You give us something that doesn't exist, we throw it back at you. Otherwise, add element at index. Oh, wait a second. You want to replace the head, huh? Or not replace the head, but you want to add that element at the head of the list. That sounds familiar. This dot add element to start? Oh, wow, amazing. Right? Again, if you write good code, if you write general generic code, turns out that it's useful all over the place. Right? Otherwise, we get the previous, the current, or let's just go with the next. And it's not a replacement, but the new node. Right? There we go. The previous, and then the next. And that's just going to be the previous dot get next. There we go. And I want to add this new node in between those. So here's previous, here's next. That's where I want to add it. Right? So previous dot set next equal to new node. New node dot set next to the next. And then you're not returning anything because it's a void function. Right? Awesome. What's wrong? Oh. Oh, what are you complaining about? That's the guy who throw. Oh, thank you. Return. Yeah, just go ahead and scream it out if I forget something like that. There we go. There. Well, obviously I'm not doing anything yet. So let's go ahead and dot add element at index. Let's go ahead and try 42 at index 0. Let's see if that works. Oops. Why are you complaining? Oh, because it doesn't return anything. Sorry. There we go. Add element at index. And then get rid of this as well. There we go. Run. Great. Index 0. Index 1, I'm going to repeat every single test that I just did. I should expect an exception. I should expect it to add it to the head. I should expect it to add it 10, 42, 20, dot, dot, dot. I should expect to add it at 10, 20, 42. 10, oops, save. 10, 20, 30, 42. 4. 10, so 3, sorry. There we go. 1, 2, 3, 4. Uh-oh. Invalid index. That seems like it should work though, right? If I've got 10, 20, 30, 40, adding it to the end here, why can't I do that? Well, because apparently I need to change my condition here. Now it's perfectly fine. Oh, not get element at index. Where is it? Add element at index here should be equal to is perfectly fine because that means that you're just adding it at the end. That might actually be another edge case, but we don't have to take care of that because our code was so nice and pretty over here. Right? It took care of that for us. Now, one last test here. Obviously, if you go too far, then no, that's not going to work. All right? Now, with 1 minute left here, let's go ahead and restore all of this stuff that we were looking at last time. Or not last time, but that started off this entire thought process here of that the array list is not good because we're always adding stuff to the beginning, always adding and shifting stuff down. Can we now get this to behave nicely? 100,000 things. Is it going to take, I think it was what, 15 seconds or something like that before? Maybe a couple minutes. I forget what the estimate was. 1, 2, 3, 4. Oh, this is at the end. Sorry, that's not what I wanted. I wanted dot add element at the start. There we go. 10. I'll just add 10 over and over and over again. Right. What took 15 seconds before with one implementation now is instantaneous. In fact, I can probably go up to 1,000,000 and it's not even going to be that much more noticeable. Right. We'll understand why next time.